So the title of today's notes, we're going to be dealing with normal distributions again, that bell-shaped curve. We're going to look at a really specific type of normal distribution today and how to find areas under the curve if given a value on the horizontal axis. It's kind of the whole idea of today. I want to review with you, because it's been a few days since I've seen you. It says sketch a normal distribution curve. The mean is 6 and the standard deviation is 2. It says to label the mean and the points 1, 2, and 3 standard deviations from the mean. That means to the left and to the right. And then we'll answer the question, what proportion of the area under the curve is less than the number 8? So let's just take a second, use this space here. You're going to want to draw a horizontal axis. To the best of your ability, draw that unimodal bell-shaped curve, normal curve. When you're drawing these and you're given the mean is 6. Where should I put that? Good, in the middle. And this didn't give me a specific problem, like I don't know if I'm talking about 6 miles an hour, 6 inches, 6 pounds. So normally I would title it and put my units, but oh well. And the standard deviation is 2, and so I would just want you to think of that as, well, that's what we're counting by. We're counting by 2's. And it says, and we'll always do this, go 3 to the left, 3 standard deviations to the left, and 3 to the right. So to go to the left, I'll subtract 2, subtract 2, subtract 2. And then to go to the right, I'll add 2, add 2, add 2. And I just chose these numbers to make our math really easy here so we could move along kind of quickly. Now the question is, so here it is, it's all drawn out, what proportion of the area under the curve is less than 8? So here is my boundary of 8. It says less than that. So I just need to maybe add all of these slices together. Let's see if we remember, and it's okay if you don't, because I probably wouldn't remember if I was a student. But we're going to see if we can remember the percentages in all of these sections, and then we can just add them together. Well, the empirical rule says right here, within 1 standard deviation of the mean, in other words, from 4 all the way up to 8, is 68%. That means that there's 34% in each of these middle slices. 34%. And then the empirical rule says, do you remember the next percentage in the empirical rule? 95%. I guess I should write them out here. Yeah, there's 95% from 2 all the way to 10. So if I take 95%, I subtract out the 68, and then I divide by 2, that leaves me with 13.5%. And then 99.7% are within 3 standard deviations of the mean. So if I take 99.7 minus 95, cut it in half, then that leaves me with 2.35%. And then the teeny tiny little tail only has 0.15% in it. 0.15, 2.35, 13.5, and 34. That makes 50%. That takes us all the way to the middle. So 50% of the area under the curve is over here. And then it wanted us to go all the way up to 8, so we have an extra 34%. So if we add all of those together, and I'm going to use a little bit of common sense, 50% takes me to the middle, and I just need to add an extra 34%. So how would we write this answer? The answer is not 84 because it says proportion. So instead of writing 84%, how can I write that as a decimal? Because proportion just means decimal form. What is 0.84? Good. So put about 0.84, because remember those empirical rule percentages, they're estimations. So about 0.84 of the area is less than 8. I don't know if that's 8 pounds, inches, miles per hour, but less than the number 8. And all I did was, and I'm going to kind of shade it in, I added each of those slices together to the left of 8. There is an easier way. You just have to be, or a different way, I should say. You just have to be really comfortable with the empirical rule, and I think it's kind of easy to just memorize the slices and add them together. Now, look closely at what I've typed right here, okay? The empirical rule is really helpful if you're being asked about one of these numbers. If you're being asked about 0, 2, 4, 6, 8, 10, or 12 that you've labeled, then the empirical rule is what you're going to use. But here's what today's lesson is about. What if I asked you that same exact question, but I said, what proportion of the area of the curve is less than the number 3? Well, 3 is not one of those tick marks that I drew. So we could estimate, but if you're asked about a number that's not exactly 1, 2, or 3 standard deviations away from the middle, you're going to have to use your calculator. So I want us to kind of explore something here. Let's fill in these blanks. All normal distributions like the one above can be converted to be the same if we measure in units of size, standard deviation from the mean. That doesn't really make a whole lot of sense to you, but I want to bring back this formula for finding a z-score. It's called standardizing. If you take a numeric value, subtract the mean, and divide by the standard deviation, you get its z-score. I want us to do this. I want us to take this curve that we drew with the 0, 2, 4, 6, 8, 10, 12. I want us to find the z-score for each of those numbers, and you're probably thinking, oh my god, I have to use that formula 7 times. It'll go by really fast, okay? We're going to take each of these red numbers that I have, 0, 2, 4, 6, 8, 10, 12, and we're going to standardize them. So here's how I want you to organize your work in this blank space so you know what we're doing. We're going to standardize the number 0, and 2, and 4, and 6, and 8, and 10, and 12. There's a reason this is going to go by quickly. You're going to start to see a pattern. You do not have to sit there and plug into the formula 7 times. Let's standardize the number 0. So if I want to find the z-score for 0, I'm going to take the number 0 and I'm going to subtract off the mean, which at the top of the page it says the mean of this data is 6. And I'm going to divide by the standard deviation of this data, which is 2. If you're good with your algebra or your numeric skills, that's -6 divided by 2, which is -3. So the z-score for 0 in this curve is -3. Let's find the z-score for 2. That would be 2 minus 6 over 2. Well, 2 take away 6 is -4. -4 divided by -2 is -2. All right, let's do the next one. Let's find the z-score for the value of 4. 4 minus 6 over 2. 4 take away 6 is -2. -2 over 2 is -1. You see a pattern emerging here. Look at our answers. -3, -2, -1. What do you think the next one's going to be? It's going to be 0. What do you think the next one's going to be? 1, and then 2, and then 3. Here's what we did. We took this information, 0, 2, 4, 6, 8, 10, 12, and we standardized it. That's how you would say it. We standardized it into what's called a standard normal curve. Now, what number should go in the middle? 0. So that 6 that was originally in the middle, when I standardized that, I got a z-score, a standard score of 0. So the mean, when I standardized everything, the mean is now 0. And according to this pattern that we found, what am I going to be counting by? 1s. So what's the standard deviation? It's the same question. 1. Yeah, standard deviation is what you're counting by. So listen really closely. When you take any word problem, any crazy word problem, miles per hour, inches, whatever, and you take all the numbers on that axis right there, like we just did, and you standardize them, every single time, what's really cool is you're going to get these numbers right here, no matter what. You're going to get 0 in the middle, and you're going to be counting by 1, which is kind of cool. So when we standardize all of the points on the horizontal axis of any problem that we look at, we end up with a mean of 0 and a standard deviation of 1. This has a very specific name to it. This is called the standard normal distribution. We standardized, we built this. It's called the standard normal distribution. It's just a really specific type of standard normal or normal curve. Down there at the bottom in the blanks, the standard normal distribution has a mean of 0, mu is 0, standard deviation is 1. That's a little lowercase sigma. So what we did isn't difficult. You might be wondering, why would you ever need to do that? Why would you want to take all of these numbers and change them? Let's kind of play with this for a second. It says, remember that original question, if we wanted to find the area to the left of 3 with a mean of 6 and standard deviation of 2, we could standardize the boundary value of interest. So I want you to look at these two pictures. What do you notice about the shaded areas in these two pictures? Are they different or the same? They're the same. So what we have here is we have our original normal curve. That's the one you drew at the beginning, the top of your notes on page 1. You drew this out, and I'm interested in finding the percentage or the proportion to the left of 3. Well, the really cool thing is, even after we standardized and we found the middle was 0 and then we're counting by 1s, I want you to notice that that shaded region is the exact same. I want us to figure out what number that is right there. All you have to do is the same thing you did for 0, 2, 4, 6, 8, 10, 12. You have to find its z-score. I want to know what the z-score is for the number 3. I want to know what number is on my standard normal curve, where 3 is over here on the original normal curve. So I'm going to take that value of 3, subtract the mean, divide by the standard deviation. That's negative 3/2, which is negative 1.5. And if you're not really strong with your math skills, that's okay. Just want to make sure everybody in here feels comfortable with this. 3 minus 6 over 2. And then you can have your calculator, if you hit math decimal, it can change it back into decimal form. So negative 1.5. If I lost you, here's what we just did. We took the original number 3, and it turns out on a standard curve, that number is negative 1.5. But the shaded area, the area to the left, is the exact same. So now I'm finally going to show you the whole entire, basically the lesson of today, is how your calculator can find this shaded region. Your calculator has to do it. You can't do it by hand, okay? So here's what we're going to do. Press second vars. Second vars. And this menu pops up. And I want you to choose the second option down, which is normal CDF. It's going to be your best friend on the test at the end of this chapter. Normal CDF. And what it asks for is 4 things. It asks for a lower, an upper, the mean, and the standard deviation. And depending on the word problem you're looking at, those are all always going to be different things. So here's what I want you to do. Look right here. This is the one we're going to put in the calculator really quickly. When it says lower, it means what is the lower boundary of your shaded area? And you might be thinking, well, 0, because it stops at 0. But do you remember us talking about there's a teeny tiny little amount left in the tail beyond 0? So this is really bizarre, but listen, for your lower, because you're technically shading to the left forever, you're going to put the lower is negative 1,000. And the reason statisticians do that is to just make sure we know we're going way out to the left forever and ever and ever and ever, and we're just going to cover all of our bases. So I want you to type in negative. Be sure you're using the negative button and not the minus button. Negative 1,000. I'll address that on the next page. Like, why is it negative 1,000? Okay, the upper. Look at what I'm pointing to. What's the upper edge of the shaded region? Where does it stop? 3. Okay, so 3. Over here in the original curve, what is the mean? 6. So mu is 6. And what was the standard deviation? What are we counting by? 2, and that was given in the problem. Now if you'll hit enter, 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 your calculator gives you the answer. This is the proportion of that shaded region to the left of the number 3, 0.07. If we round to the hundredths, it's 0.07. Do you think that we're going to get something the same or different over here for the proportion of this shaded region? Any predictions? Should be the same. Wouldn't that be if the area under any curve is 1 and the shaded regions visually are the exact same size, we should get the same thing. Well, let's try it. So this time, hit second vars, normal CDF. Second vars, normal CDF. Now look at this picture. We're shading to the left forever, so we're still going to always use negative 1,000 if we shade to the left forever. If we shade to the right forever, we'll put positive 1,000. But this time, what's the upper value on the standardized curve? Negative 1.5. What's the mean of any standard normal curve? 0. What's the standard deviation of any standard normal curve? 1. And your calculator actually defaults to that. Hit enter, 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 and we get the exact same thing, 0.07. And that goes down here. What do you notice? We get the same answer area, whether the value is standardized or not. Whether the values are standardized or not. And again, think of standardized as finding the z-score for all your stuff. So guess what? In on-level statistics, because this is not an AP course, so here's something really cool. In an on-level statistics class, if you get the same answer both ways, you don't have to do the extra work. But there is a reason that I showed you all of that. I'm thinking ahead as your teacher, okay? So I didn't waste our time. But if your calculator can use all of these numbers to find the answer, there's no need to standardize everything to find the same exact answer. It just is going to feel like extra work. But it's a skill you need in the future, okay? So turn the page and let me kind of answer some questions you might have. Why did I randomly say use negative 1,000 as the lower boundary? It seems really random. And we choose negative 1,000 because it's many standard deviations below the mean. And all that means is, again, I just want to cover all of my bases. I'm shading technically to the left forever, so I want to make sure the calculator knows not to stop, too soon. It gives more of an accurate answer. But let me show you something. What if I, instead of putting negative 1,000, what if I forgot and I put negative 100? Does it change the answer? Okay, what if I got carried away and I accidentally put negative 10,000? Does it change the answer? No. So don't get too hung up on how many zeros it has. Just go way far to the left. But something that happened to my AP students that may happen to you on an upcoming test is this. Listen really closely. You're going to memorize negative 1,000. But you're going to have a word problem talking about people's salaries and how much money they make every year. So we're talking about, I don't know, hundreds of thousands of dollars. So if we're talking about hundreds of thousands, negative 1,000 isn't going to cut it. So use a little bit of common sense at the problem you're looking at when you draw your picture. And I'll say more about that later. Okay. Why would we take the time to standardize if you can get the same answer in the calculator either way? And it's because you will need the skill of standardizing, like that little z-score formula, in the future. So when I cover that again in upcoming chapters, I don't want it to be brand new then. All you learned today about that was, hey, if you standardize everything, the mean is 0, the standard deviation is 1, you can put it in the calculator that way, or you can just take the numbers out of the word problem and do it that way. You don't really need to read this box because I've already told you all of that, okay? Let's practice. All we're going to do is 6 examples in a row, and you're going to see how fast you can put these in the calculator, all right? But listen closely. I need you to draw a picture every single time and show yourself what's going on. Example 1 says, many studies of automobile safety suggest drivers must make emergency stops. The stopping distances follow. Okay, blah, blah, blah. This is important to me because I know what shape my curve is. It's not skewed, it's normal. Okay, and it says that I'm reading along as a student, and I notice the mean is 165, and the standard deviation is 4. We've seen this problem before, I think. Marta is driving one car. She spots an accident 170 feet in front of her, and she needs to make an emergency stop. What percent of cars could stop in less than 170 feet is the question. Let's draw a picture. So stopping distances from the time you slam on the brakes till the time your car actually comes to a stop can be modeled with this normal distribution curve. The average distance that it takes this model of car by the time you press the brake to coming to a complete stop is 165 feet. That's the mean. The standard deviation is 4. So count by 4s. Take a second if you need to crunch your numbers in the calculator. That's a skill that you should have by now. Subtract, subtract, subtract 4. Add, add 4. And I'm going to go ahead this time and title it since I have stopping distance. One of the best things that you can do for yourself is label, because then you'll understand the meaning of the numbers. We're talking about how far it takes a car to come to a complete stop. Well, she sees an accident 170 feet in front of her. She slams on her brakes. I want to know, kind of think of it as her odds of being able to stop in time. Is she going to hit these people? Is she going to be part of the accident? Or is she going to be able to stop? Well, it says what percent of cars could make the stop in less than 170 feet? Figure out about where 170 is. And it's just to the right of 169. And I want you to draw your boundary line. So the first thing is draw your line where the number in the problem says. Then decide which way you're going to shade. And my key word here is less than. Would I shade to the left or to the right of 170 feet? To the left. Gosh, that seems like a large area. So I should get a large proportion or a large percentage. So in the end, if I get something like 13%, I'm going to know I did something wrong. Okay, your calculator is going to do everything for you. That's all the work that you have to put into it right there. The calculator is going to tell you that because you're going to hit normal, CDF. What will you put as your lower? Ooh, I don't know. Which way did we shade? To the left forever. So what will you put as your lower? Good, negative 1,000. Maybe you want to put that in your picture over there. What will your upper be? Where does your boundary stop? Good, it's the problem, the number in the problem. What will you put in as mu, or your average? 165, that was given to you in the paragraph. What will you put as your standard deviation? 4, that was given to you in the paragraph. How easy is this? The most time-consuming part is drawing the picture. Negative 1,000, 170, 165, 4, enter, enter, enter. I got 0.89, but it asks me for a percentage. What percent? Okay, so let's make sure that our answer goes out to the hundredths. So if I move that decimal over, I have about 89.44% of cars can stop in 170 feet or less. So she's got a pretty good chance of being able to stop in this model of car that they're talking about. Her odds are good. She's got about an 89% chance of being able to stop in time. Why didn't I teach it last lesson? Why would that have been helpful for the empirical rule? Yeah. Yeah, so could you do a problem like this faster now? Do you have to really memorize all these percentages in the slices? And you might be thinking, no, I can always do it in the calculator. Yeah, but you know there's going to be multiple choice questions that require you to think this way. You can use your calculator whenever you can, but I still want you to know about the empirical rule. So that's good. I'm glad you asked that question. Most of the time you can get away with this. So let's see how fast we can go now. When professional golfer Rory McIlroy hits his driver, the distance the ball travels can be modeled with an approximately normal distribution. The mean is 304 yards. This standard deviation is 8. I'm going to stop right there and draw a picture. Drawing a picture is so important that on the statistics AP exam, you don't get full credit unless you've drawn the picture. So that's not a funny little thing Mrs. Lewis wants you to do. It's just a thing that you need to do for these problems. Draw it out. The mean is 304 yards. This is his driving distance in golf, specifically in yards, how far he can hit the ball. And then standard deviation is 8, so count by 8. And I'm going to grab my calculator. -8, -8, -8. It's faster for me to do that than to subtract in my head and possibly make a mistake. And then add 8, add 8, add 8. Now I got to go back and read what it's asking. On a specific hole, Rory would need to hit the ball at least 290 yards to have a clear second shot that avoids some trees. What percent Gotta make sure our answer is in a percent, not a decimal. What percent of drives will travel at least that 290 yards, and is he likely to do that? The first thing I need to do is draw my boundary line, and I'm going to use the number in the problem that it's asking me about. It's asking me the odds of hitting the ball at least 290 yards. 290 yards is somewhere between 288 and 296. But here's the trick that your brain might play on you. You see the word least, so you might be thinking less than. So you might shade to the left on accident, but stop. If you want to hit the ball at least 290 yards, that means you want to hit it 290 yards or more. Like if he hits it 308 yards, that'd be fantastic. I do. Did you shade to the left? Okay. That doesn't really change anything other than what lower and what upper we're going to put into the calculator. So again, the calculator is going to do all the work to find this. I always draw an arrow to the shaded region. Before you grab your calculator, write this down. Tell me what you're putting in the calculator. Tell yourself before you pick up the calculator. Let's think about this together. The lower, is it just going to be negative 1,000 because it's what we've been doing? It's not negative 1,000. Did I shade to the left? No. Is the lower edge of my shaded region at a positive 1,000? Oh, it's at 290. There you go. So the upper is going to be 1,000. And the mean and standard deviation, you don't really ever have to think about because it's in the paragraph. The mean was 304. It's also in your picture. The standard deviation is 8. So by writing it down, you just give your brain one more second to pause and think about your lower and your upper. Now, if you shade the wrong way, you're going to do the wrong lower and upper, and your answer is going to be wrong. So, second bars, normal CDF. The lower is the 290. The upper is going to be positive 1,000. The mean is 304 yards, and the standard deviation is 8 yards. Enter, enter, enter. That's like 95.99%. About 95.99% of his drives travel at least 290 yards. Does he have a pretty good chance of that happening then on this particular course? Yeah. He is likely, let's put very likely. He has like a 96% chance there. He is very likely to have a clear second shot. I just go back and see what they asked me. Is he likely to have a clear second shot? He's very likely to have a clear second shot. The end. The only part your brain is going to have to work on is which way do you shade? What's my lower? What's my upper? By the way, before you turn the page, if 96% is in the stripy area, what percent is in the non-stripy area? That's going to be a skill that you need later. If 96% of his drives are more than 290 yards, what percent of his drives are less than that? It's really easy. 4. Yeah, because both the stripy and unstripy add together to be 100. Okay, let's go faster on number 3. This is my favorite kind of problem, and you're going to see why. It's even easier. On another golf hole, he has the opportunity to drive the ball into the green. If he hits the ball specifically this time, they're being very specific. It's not a more than or a less than. It is literally he has to hit the ball between, there's like a sweet spot, between 305 and 325 yards. What proportion, so we'll leave it as a decimal this time, of his drives fall within that range. I want to see how likely it is that he hits this sweet spot of 305 to 325 yards. Well, I'll allow us to do our picture a little bit sloppier this time. If you'll at least put the 304 in the middle, then I'll let you put 305 and 325. I won't make you actually label the standard deviations because we've already drawn this picture a second ago. But this is the region that I care about. This is where he has to hit this ball to get it onto the putting green. This is my favorite kind of problem because you don't have to really worry about which way you're shading. You don't have to worry about negative 1,000, positive 1,000. It literally tells you your lower and your upper. Your lower, sometimes you might see people write it like this instead of in the parentheses. Your lower is what? Can anybody tell me? What's the lower edge of the shaded region? Yeah, it's just the numbers they give you in the paragraph, and the upper is 325. And the mean is 304, and if you forgot from a second ago, the standard deviation is 8. Thank you. So you may want to write, if you prefer writing it like this, instead of in the parentheses, you can do that. Let's see what proportion of his, based on his past games, what his statistics are here. About 0.45, about 0.45 of his shots are between 305 and 325 yards. So if I asked you how likely it is, I mean, he's got less than 50% chance, so maybe not so hot. You guys, we're doing great. Example 4. I wanted to throw in a problem that you might see on the test. Notice it's a multiple choice problem. You could see this very same question on the test. The company produces ceramic floor tiles. They're supposed to have a surface area of 16 square inches. But because of the manufacturing process, like the machinery, the actual surface area has a normal distribution shape. The average surface area, the mean, is 16.1 square inches, and the standard deviation is 0.2. Do you see that you can be totally successful and have no idea what standard deviation is right now? And that's fine with me. The proportion of tiles produced with a surface area of less than 16 is what? All right. I'm a student, and I'm just going to go as fast as I can. The mean is 16.1. And because of the machinery, the tiles are not always going to be perfect. There's going to be a little bit of variability here. Standard deviation is 0.2. So minus 0.2, minus 0.2, minus 0.2. Plus 0.2, plus 0.2, plus 0.2. Surface area in inches. Now, on a multiple choice question, do you have to do all of this? No, not if you're just a calculator whiz, but it's probably going to be helpful to avoid making a mistake. I want to know the proportion that are less than 16.0. Less than. I have to know that means shade to the left, which is going to influence what I put in the calculator. Because my lower is going to be negative 1,000. My upper is going to be the 16.0 because I shaded to the left, so the very upper edge of that is 16.0. I'm going to put the mean and the standard deviation that were given to me in the problem. And then I'm going to get my answer, and we're going to circle it and move on. Second bars, CDF. Take a second and see what you get. Don't say it out loud. This is a good chance for us to all kind of see if we're understanding. This lesson's pretty easy. Thank you. All right, is it A, B, C, or D, or E? B as in boy. The person who put E accidentally shaded to the right. As if you notice, these two added together equal 1. So this is to the right. So that would be if the question said more than 16.0 square inches. Just as a little extra info there. All right, example 5. Birth weight at a local hospital. Birth weights have a normal distribution. The mean of these little babies is 110 ounces at this specific hospital. The standard deviation is 15 ounces. What proportion of infants are under 95 ounces? Don't get lazy. I know some of you aren't even drawing pictures anymore. Birth weight in ounces. Counting by 15s. What proportion of infants have birth weights under 95? What's interesting to you guys about that? Well, it may not be interesting. What do you notice about the number this time? The number 95. It is one of the marks. You could use the empirical rule. You probably don't really like that anymore now that you have this cool little calculator thing. So by all means, use the calculator. If you can, why not? It can make you do more work than you have to. Lower, upper, mean, standard deviation. The lower is going to be negative 1,000. The upper is going to be where I stopped at 95 ounces. The mean is 110 ounces, and the standard deviation is 15 ounces. Now, if we did use the empirical rule and we added our slices together, we'd add 0.15 plus 2.35 plus 13.5, and we'd get an answer of 16%. Let me just show you. If I use the empirical rule, but the calculator allows us to be more accurate, so there's actually a benefit to doing it in the calculator. You should have gotten something like, does it say percent or proportion? Okay, proportion. So about 0.16. Well, I guess if you round it, it's the same, huh? So about 0.16. Don't put percentages unless it asks you to. Of infants weigh less than 95 ounces. So a really good question was asked earlier. Why would we even need the empirical rule when it's for a problem like this? You have to know it for this. You finally get to see there's no way around it. Watch. IQs among undergrads at this college are normally distributed approximately. The mean is 110. Well, normally, then it tells me the standard deviation, and this one doesn't. It says about 95% of undergrads have IQs between 100 and 120, and it's actually asking me for the standard deviation. So let's draw what we know. The average IQ for undergrads at this college is 110. But I can't label anything else because I don't know the standard deviation. But here's what I do know. 95% have IQs between 100 and 120. That's a number out of the empirical rule. The empirical rule says this: 95% of this data is going to be within 2 standard deviations of the mean. That means 2 below, all the way up to 2 above. 95% of the data lies between those 2 IQs. And it tells me those 2 IQs are 100 and 120. It's like a little logic puzzle. Now, how do we find the standard deviation? Is it just 10 because now these are labeled 100, 110, 120? It's not 10, and I promise that would probably be an answer choice. What are we counting by? We're counting by 5s. Very good. So the standard deviation from like here to here, just one standard deviation is 5. You can use a symbol and write it that way. You can use SD for standard deviation. But since we're talking about IQ, there's not really units. We can't put pounds or inches or anything. So the standard deviation is 5. Very good. So the empirical rule, sometimes we couldn't use our calculator on this one, just to show you. You guys did a fantastic job. We're done with the notes.